First, let's discuss a little bit about the use case. It's a data set from 2016, from 1 month, December, and it's the New York City Taxi Green dataset. And this is basically information about cab rides that were taken in New York City by the Green Line taxi. Maybe that most people are not that familiar with it, but it's a little bit the same as the yellow cab. But the green cabs, they also go outside of Manhattan. And this person created a data set from it, for it, where we are going to try and predict how much tips the customers will leave at the end of their ride. There's a little bit of a write-up here as well. And this person already did some selection for us because it's known that this data set has data drift inside of it. So that's also why we decided to pick this one. So thanks for that. The real data set source can be found on this link. It's DLC data recorded. They gather a lot of data for a lot of different months. And it's all about cab rides. And we just picked this 1 month that was also used in the analysis of this person. And then there's also a data dictionary explaining a little bit more of the columns and which data we can fetch. So I already read in the data because I thought, yeah, maybe if everybody's going to read in the data itself, the platform might maybe not be able to handle those amounts of requests. So I already did that. So this is the URL that basically links to the Green Taxi ride trip record of 2016. And then there are some columns that I already pre-selected that are relevant for what we're going to do here today, which is the pickup date. So the date that the customer actually enters the cab, what the location is, the pickup location, the drop-off location, the trip distance, and then the vendor ID, that is who sold or who collected the data. Then there's a payment type, a fare amount, and a tip amount, and it's the tip amount that we're going to go and try and predict based on where the customers come from, how long they spent in their car rides, and how much they had to pay at the end. There's a small note here about to ignore, because you can pull in more data if you'd like. There's a small note about the total amount, which is also present in the data sets. But if the total amount is present, you have the fare amount too, then you can basically subtract the fare amount from the total amount and measure the tip amount deterministically. So for the sake of this exercise, it's important that you ignore and not pull in the total amount, or at least not use it as a feature. So let's have a quick look at that data. We can see here, of course, yeah, it's the first day of December, and then here at the end, last day of December. We can also see that actually the data seems to be ordered by day, but then here we actually see that it's maybe not ordered by minutes. So that's something to bear in mind. And then we have our different features and our target and all of the information for it. Based on the work that the other person had already done that shared this public data set, who also mentioned about the tip amount to be removed, is to only select credit card data, because only there we actually have the tip amount registered. So we're gonna select the credit card, the payment data equals 1, because that's the credit card, and then after drop that column 2, because it wouldn't be needed. Then we have to perform some data cleaning as well, which is sorting the dates, resetting the index, and then setting some columns to categories. Here's a small snippet of other category columns if you decide to pull in all the data. That's important for training the machine learning model, and also later on how we want to detect data drift. It's important to know what type of data type it is. And since we pulled in a Parquet file, these data types didn't get ported over with it. And we can also do some quick feature engineering. Like feature we can build is, for instance, take the pickup time and then extract the hour to actually have take the time that they got picked up, then which contains the date, and then extract the hour to know when people are gotten picked up. Then the next thing we're going to do is we're going to split the data, and we're going to create a partition. And since this is 1 month data, we're going to use the first half of the month for building the machine learning model. And then the second half of the month, we're going to treat this as the production data, or the data that normally we would feed into the machine learning model when the model is deployed. So we set these dates, we create a partition column, then we can set what our target is, also quickly which features we're going to use, and basically all the data are features except the partition column that we just created and the data column and the target, and then we can split accordingly. So we'll create a training set and a test set and then a production set. And right now we're just going to ignore the production set for the time being, because we need to be building the machine learning model first. Just a few things that are important, since we're trying to predict the tip amount that the customers will leave at the end of the ride. It's important to kind of know how that distribution looks like. It's on average, people leave $2.3. You might want to see at the box plot as well, because we can see that actually the data is, the variance on it, it's not that big, but we see that there are some outliers. So I'm going to clip the data here so that it only uses like 95% of the data. We also see here that there's a negative value, which is interesting. That's maybe when the driver decided to tip the customer. But let me quickly remove that actually to get a better view of what like the majority of the data looks like. And then we can see here actually that there's potentially a lot of zeros as well, people not leaving a tip. I'm gonna make this a little bit, yeah, exactly. I'm gonna make this a little bit more granular because this is very interesting. And it's kind of what you would expect this type of distribution to see, that there's people not tipping, and then there's other people that start to be tipping, but actually tipping very low, it's not that common. And we're in New York City, so it's probably you either tip or you tip a little bit more. And if the data is structured like the first thing as a data scientist I would think about is, okay, let's build a machine learning model. First, a classification on whether somebody tips, and then a regression for how much, and then maybe also some transformation to make this data a little bit more normal. But we're going to ignore that for the time being, because we're not about building the best model right now. We want to deploy the model as fast as possible and then see how it's going to behave in production. So quickly describing the other features as well, the categoric features, we can see that the drop-off location has more unique values than the pickup location, which also makes sense because the drop-off can be outside of the city, and then cab drivers usually stay around a certain point of area. Vendor ID, there's only 2 vendors. And then the trip distance is 2.9 on average miles, not sure. The fare amount is $12, and then the average tip on that was like, I think, $2, $2 and a little bit. And then we also know that most people actually on average travel around noon. So next up, now that we have a quick view about the data, we're going to train a machine learning model. We're just going to use the standard settings of the light GBM, and then make predictions. How we're going to evaluate it is, because we're doing a regression, we can make like a very naive prediction as a baseline, which would just be the training mean, and then use that prediction for both test and training. And then, of course, in this case, we're going to pick mean absolute error as a performance metric, because there are some outliers and we're not squaring any of the error terms. So then this is a little bit more robust. And then we can also measure the error on the baseline and also on the machine learning model itself. Quick report to check how that model performed. So we have the training performance here, which is almost 1, and then a test performance 2. So that means that the model is actually not that overfitted on the training data, and we're still doing better, significantly better than just predicting the mean. When it comes to the feature importance, we see that the fare amount is the most important feature, which in a way makes sense, because tip is often just a percentage, or that's at least how I tip in the US, because I come from Belgium and there we don't really have a tipping culture. So I usually just do like 10, 15 or 20%. So it makes sense that that has a high impact on the tip, I would say. Then the next thing is the drop-off location, the trip distance, the pickup location, also pickup time, and then the vendor ID is actually not that important. Drop-off location being more important than pickup location, that's also interesting. Probably it has to do with the fact that that's at the end of the trip when you decide whether you want to tip somebody or not. But it's good to have a view on how important these features are. Now, then we're going to deploy the machine learning model. And since we're just doing an analysis on historical data, we're just going to predict on the production data and kind of mimic that this would be similar to being inside of production. Now, then if we want to analyze the model performance in production, we first need to do some quick formatting because there has to be a reference and an analysis data set to be created in order for NannyML to properly assess and see what's up with your performance. I went quite elaborate about it, but that's just to drive a point home of which parts have to be present to do proper monitoring. So first of all, we're going to take the test set as a reference. What does that mean? That the test set is created in such a way that it should represent how the production data will look. That is, it should mimic it. So, and then on the test set, because that is truly historical, we know the performance, and this can resemble the expected performance. And that's why we're going to use that as a reference to compare our production data towards. So for that, we need, of course, the test set features. We also need the predictions. And since it's historical data, we also have the ground truth. And I'm going to go back to the initial data set and also fetch the time, because this is an important component. When we move to production, we want to see how things change over time. Then we are going to set up the analysis data, which is just the production data. So all of the data that goes into the machine learning model after it has been deployed. And we're going to collect the same thing, which are the features, the predictions. So what goes into the model, what comes out. And then usually you don't really have access to the ground truth in production. That's just the reality. Most use cases, when they predict, it takes a long time for you to gather the ground truth or to gather the actual resolution. Here in terms of tipping, it might be that if we're, for instance, for Green Taxi, how their payment systems are set up, that they instantly know how much was being tipped. But I can totally imagine that that is in some way regulated, that the tip has to go directly to the driver itself, and that it might take a while before that information can actually be gathered, and that it may be even something that the driver has to report later. And then we don't really know at the time of making the predictions what the ground truth is. And this is a typical use case where the ground truth is delayed or absent. So we're going to assume that that is the case, because that is most often the case with machine learning models in production. And then that kind of is a good way of mimicking how it would look like. And then we do the same thing for getting the data in the analysis. And then we do the same thing for getting the data in the analysis. And then the first thing we would want to do is get a view on how our machine learning model is performing in production. Now, the tricky thing is, because there is no ground truth, we cannot actually measure the performance. Because normally would you just compare the y-pret in production with the y-true in production. But since we don't have that, we'll go and have to estimate the machine learning model performance. There's a link to 2 articles because these are algorithms that we developed to kind of get visibility on performance when the target data is absent. And that is what these algorithms, I'm not going to go into detail, just read these blog posts and then you will kind of understand how they're built. For regression, we're going to use direct loss estimation. We'll have to say whether a metric is of interest, how much we're going to tip, what the not how much we're going to tip, but what the actual mapping is of the y-true and the mapping of the y-pret. Earlier, I defined the features. It's important that we also provide this mapping to the algorithm, the pickup date, and then on which time we want to chunk. And chunking is basically the granularity. So the chunking, that is basically what we're going to aggregate the data over. And since we have 1 month of data, we are going to pick day, and then we will get our results per day. The next thing what we will have to do with this algorithm is fit it on the reference data. So this algorithm is going to leverage the features, and then it's gonna basically subtract and create a loss. That's why it's called direct loss estimation, the predictions from the test, and that is then what this algorithm will predict. So that for new predictions in production on the analysis, we will also feed it the features and also the predictions, and then we're just gonna estimate the loss, and from that we can actually reconstruct our error metric. I'm just quickly gonna run that. And then we can see how the estimated performance looks like over time. So this is the test set where the performance that we consider as reference and where it's working as expected. Then here we deploy the machine learning model, and then the second half of the month, we're actually making predictions. And we can see that here during these days, the performance actually went over the thresholds, and this is a clear sign that we have performance issues. And the next thing, and then of course, this was of course as part of the data set. The next thing, of course, is to go and figure out what went wrong here in this period so that we can understand. And ideally, we do that right in time when these alerts are happening. But right now, because this is a historic analysis, we're going to do it right now because we still want to understand what went wrong in that period. But at least right now, by using DLE, we have a view on what our expected performance was, so that we can drill down and use the multivariate and the univariate data drift detection techniques to delve in deeper a little bit. Also for the multivariate and the univariate, there's 2 links to some articles that explain how these algorithms work. So first we're gonna do the multivariate data drift detection. Same thing, we'll have to apply the features, like what goes into the model, the date, time column, and then also on which granularity we want to chunk, because every chunk here is a day, and then the metric is aggregated for the observations that happened during that day. How do we pick the chunking granularity? For this use case, it's actually important that we pick it on a day. There's other ways to chunk as well. We can chunk on month, but we can also decide to choose a chunk number and that we just say we want 10 chunks, or we can just say every 5,000 predictions, we consider that a chunk. But since this is gap hailing, there's probably some types of trends that occur during a single day and then repeat itself the next day. So then it really makes sense to actually collect all of these observations per day. In the meantime, our multivariate data drift algorithm has run. And unfortunately, or fortunately, we actually don't see any data drift. And the reason for this is that this is PCA-based multivariate data drift detection, and PCA works specifically well with linear relationships. So my guesstimate is that in this period when the performance is dropping, those relationships are actually not changing that much, or they might, the more complex relationships might be changing, but we won't be able to capture them. Why am I still running this? Because usually if we have more complex machine learning models, this is a thing to run, and specifically because this multivariate data drift detection actually also captures the relationships between the features. There's also other ways to do multivariate data drift detection, like autoencoders, and they can capture more complex relationships, but this is just for the sake of completeness. And the whole idea about doing multivariate data drift is that it's an aggregated way of doing a root cause analysis, but we want to actually know on a feature level what went wrong and specifically what happened in these few days, so that we can tie everything together and know what's up with it. So for that, we're gonna do univariate data drift detection on all the features. And then we're also just gonna quickly display all the features and see how the potential drift has happened. And first of all, we can see here that in this period, we get some alerts as well, but there's actually no real impact on performance. And I can already see why that's the case, because it also happens with the drop-off location. And that is probably actually, if you see, this is quite similar to here. And that is probably the weekend. And we can see here that there are some trends in this data, that there are some weekdays, presumably. And the whole idea is because this is a very small data set, how this distribution looks like, it's probably something that's gonna get flagged by univariate drift alert, because it's just on a feature level and it's a imperfect test. And that's why it's so nice that if we have this algorithm, because this algorithm does capture more complex things and also takes the impact on performance into account, because this data drift did not impact performance. And the reason being is because it's a weekend and we have observed a weekend in the past. So we actually know how to deal with this. And that's why we're only going to focus on this area and only try and explain this area, because here our machine learning models actually knew how to deal with it and actually worked perfectly well. And then we can see here, maybe the first thing is that the pickup location has drifted here in these parts. And then also we can see here that the drop-off location also gave some alerts during this period, which is fairly interesting. If you look at the trip distance, that hasn't really changed that much. Also, the vendor ID stays fairly constant. Same for the fare amount. The pickup time has changed as well. And I think this might actually be the feature to look into a little bit more, because we can see here, specifically, we're here in these 3 days around December 23rd, 24th, and 25th, that our model is not performing that well. And we can actually also see that here significant drop in the time people get picked up. And this is, of course, very interesting because December 24th is the holidays and it's Christmas. And typically in the US, I think this is actually also a Friday in 2016. So this is not a weekend day. These 2 days are, but they are holidays. And in our training data, the week prior, we didn't see any holidays. So the whole idea is that then this data is new. The patterns that are observed here are different. Maybe it's different type of customers that want to go to different locations indeed, that also get dropped off somewhere else and that have different tipping behavior as well. And that is exactly what we're picking up on here. And it's considered data drift because in our model, the whole concept of a holiday doesn't exist. So this might be considered a little bit of concept drift. Now, a holiday might be similar to a weekend. So that is why we are still able to pick up some of the changes there, and our model can deal with it in some way, but not fully. And that is, of course, what we then as data scientists try to do, is that we try to use this univariate data drift detection to piece together what actually happened here during this period, and then we can come up with a way to find actual resolutions. So the first thing that I want to touch upon is false alarms. And we're going to take the vendor ID here because with the Jensen-Shannon distance metric, we don't see any alerts here. And I'm going to switch up the metric and also view that as well. I get a deprecation warning here. Well, we can just ignore that. But it's very interesting to see, because if we pick a different statistic, a different way of measuring the data drift, we can actually see that we get some alerts here. And this is something that happens so much because these statistical tests, they are repeated day over day on a lot of features in general, and they're just very sensitive by nature. And even switching to a different methodology here right now gives 3 alerts. And these 2 alerts are actually not coinciding with an expected drop in performance. So it's really not something to worry about. And the reason being also why I picked this feature actually is because it's not important. Like this contributes almost nothing to the machine learning model. So when it's shifting, and then the expected performance is also not impacted by it, I as a data scientist don't really want to get notifications for this. And that's why it's so important to really obsess over the performance of your machine learning models first. And then when the performance is deteriorating, to actually go and use these types of techniques to do a root cause analysis and not as an alerting system itself, because the amount of alerts that you will get will be overwhelming. And that is kind of a way to deal with it. And that's also why we develop these algorithms to get a view on performance first when the ground truth is not available. If later the ground truth comes in, what I'm going to do here is actually assign it to the analysis data, because we have the ground truth because this is just a data set. Then we can also measure the real performance. And we can see that here the real performance actually also significantly went up, and that our model wasn't really able to deal well with these types of holidays. Now, the interesting thing is that we weren't able to fully capture the impact with our performance estimation. And that's because the performance estimation only takes into account data drift. And here, because there is no notion of a holiday inside of the machine learning model, there's a lot of concept drift happening. And the difference between the expected performance and the actual realized performance in this case can be considered the concept drift. Why are we then still be able to pick up some of the misperformance is that concept drift very often just co-occurs with some type of data drift, and there is also an interaction effect between the both. And that is exactly what we're able to pick up on here. And that today is an assumption from this algorithm that it only works, that it only can be 100% trusted in the cases where there is no concept drift. And for in order to take concept drift into account, we'll of course need to be doing concept drift detection as well. And that's something that we're working on. But at least we got to get an alert and a notified for this that our machine learning models were failing. So if this was running in real time, we could have taken actions and potentially resolved some of the issues. And then there's two other ways of looking at monitoring performance, and specifically data drift, which is measuring prediction drift and target drift. It's usually also a way how people tend to look at their machine learning models in production. And then this is very interesting, is that if we look at the actual prediction drift, the model output distributions didn't really change significantly. And of course, we did have model failure, but that doesn't necessarily mean that is visible in what our model outputs and how the distributions are impacted. And if you look at the target feature itself, also how much people are tipping, that also didn't really change that much. And that's why it's so important. And that's also why I leave these things as an afterthought, because at the end of the day, prediction drift and both target drift are univariate drift detection methods again. So we're using statistical tests. And these tend to be not always that reliable or that performant, because we could still actually make mistakes.